Hello, my name is Alexander Gabriel and I will be explaining the demo paper XR Carousel, a visualization tool for volumetric video. In this presentation I will give a brief description of the virtual interactions that we want to achieve, the setup and goals of the paper, and the actual demo. I'll also show a video, give a summary of the encodings and talk about our takeaways and our future work. So in recent years we've seen interactions and social meeting rooms in VR and virtual environments become increasingly more popular, with big companies like Facebook and Microsoft launching products, as well as many smaller companies. And what we see is that typically users are either represented with photorealistic representations of themselves or avatars. We think that for immersion purposes, photorealistic avatars in 3D are essential, even though they are difficult to capture, encode, and transmit in real time. So with this context, we can look at the setup and the goals of what we wanted to achieve in this paper. So again, going back to these photorealistic representations, we know that they are difficult to capture, encode, and transmit. And what we wanted to do here was to really analyze what the options were in the encoding. So what we've done is made a capture setup and encoded with multiple different encoders the raw capture to see what the results are. So in this paper we really focus on the different encoders, the latency that they give, the bit rates, the maturity of the software itself, and of course the visual quality that we can then view when in a 3D environment. On the right on this slide you see our setup. So we have a user with two Kinect cameras. The Kinect cameras capture 16-bit depth and 8-bit RGB each. And that's the raw format that we will use. For some of the encoders we've used just the video captured by the Kinect, and by others we've joined the two cameras into one point cloud. Here you see the whole experiment pipeline that we have. So on the left to the right we have the capture and we have the raw data. We have the conversion to the different data structures, and here you'll see the video, the point cloud. In the encoding, what we've done is encoded at multiple different bit rates for each of the encoders, decoded and then converted for rendering and visualization in Unity. The idea here is that then we can view the difference between the different encodings and compare with the bit rates, the encoding times, and also with the visual quality. So the carousel itself is basically a 3D environment that you can see here below. It's a 3D room where we can place the 3D representations after they've been decoded and cycle through them to compare the quality. This allows us to both always be in the same place and view the video or the point clouds, but also have a camera on a kind of rig, so we can always have exactly the same viewing angles of the outputs. I will show a short segment of the video now. I invite you to see the full video on the link below. You can also find it in the paper. But you can see that the user is there in the raw format right now, and then we can cycle through to the other bit rates and to the other encoders that we have. And you should be able to see the difference in quality, more or less noise due to encoding. So I'll quickly go over the different encoders that we've used and some of our takeaways. So in the video encoding we've used VP9 with FFmpeg, and the reason we did this was because of high bit depth support and the maturity of the encoder. So I'll remind you that the Connects output a 16-bit depth image, and so we've converted that to 12-bit and encode that with the VP9. And we've separated the RGB and the depth values, having the RGB fixed at 2 megabits per second for both the left and the right, and the depth then with variable bit rates. The reason we did this is because we are quite familiar with how RGB coding works, and we really wanted to focus on what the difference was when the depth had different bit rates. So you'll see on the table below the 4 of those megabits in each of the different bit rates are for the RGB, and the rest is for the depth. What we see is that the bit rates were quite acceptable, but the speeds, the encoding time itself was quite low. We think that with hardware encoding this problem can be solved. Regarding artifacts, you'll see that there are many artifacts in the areas where there's a lot of detail. This is due to the way that the encoder tackles the depth. And we also noticed that because we had a fixed bitrate also for the depth, there was a ramp up to the bitrates that we had set. So in the beginning of each of the video sequences, the video encoded sequences, the quality is a bit low in the beginning and then improves. For the VPCC encoding, we used MPEG's VPCC, TMC2, with a HM16 video encoding base. We had many problems with encoding the 400 or so frames, with the encoder crashing multiple times, so we ended up encoding it in batches of 32 frames, which was the cop size. The results were quite impressive in terms of the bitrate. Of course, this came at a cost of time. We hope that as the encoder and the technology matures, this can become a viable option. Overall, there were still some artifacts, but the results were quite compelling. Finally, the DRACO encoder. So DRACO is an encoder released by Google, and it compresses each frame independently, meaning that it only uses intercoding tools. There's no output bitstream like the other encoders. Each frame is actually output separately. And you'll see that the bit rates are quite large, which we expected already with the intercoding tools, and the time was also far too high for real-time use. So, what are the takeaways in the future work we want to do with this after this paper? Well, we've developed a tool where we can easily visualize the encodings of 3D representations of people, which makes it much easier to evaluate the different bit rates and do subjective testing. From the encoders, we see that video encoding is definitely an option right now, as long as we move towards hardware encoding or faster software encoders. VPCC has extremely low bit rates, but still has to mature, so that real-time use is a possibility. And we think that DRACO is poorly designed for real-time use for 3D representations. So in the future, we plan on using this tool to evaluate further other encoders and do subjective testing. Thank you for your time, and if you would like to contact us, please send us an email. Thanks.